In this video, we are going to find non-negative integers x and y such that xy minus 7 all squared equals x squared plus y squared. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. My first approach to solve this problem will be to use some algebra and try to establish some difference of squares. To do this, I'm going to expand the left-hand side. So x squared, y squared minus 14, xy plus 49 equals x squared plus y squared. Then I'm going to add 2xy on both sides. So then the right side will have x plus y all squared. While for the left, we have x squared, y squared, minus 12xy plus 49. Then you notice that if we just focus on the first two terms, and if we add an extra 36 on these two terms, then we'll have another perfect squared, which is xy minus 6 all squared. So to do this, I'm going to take out 13 from the 49, which means I have 49 becoming 36 plus 13. Then I can include the plus 36 with the first two terms. So then I have xy minus 6 all squared plus 13 equals x plus y all squared. So that x plus y all squared minus xy minus 6 all squared equals 13. Then we can factorize into sums and differences of these two expressions. And the product is 13, a prime number. Now since x and y have to be integers, that means both parts of the product at the left are integers, and the product is a prime. So then there are only very few possibilities. So either we have xy plus x plus y minus 6 equals 13, 1, minus 1, or minus 13, just the positive and negative factors of 13. And for the other part, you just divide 13 by the possible value at the top. So we have 1, 13, minus 13, and minus 1 correspondingly. To solve this in a quicker way, you don't have to solve them individually. You can just try to add or subtract the equations. If you add, then you will have 2 times x plus y is 24, sorry, not 24, but 14. Or minus 14. Then you can divide both sides by 2. And you have plus or minus 7. Whereas if you subtract, then you will get 2xy minus 12 equals either 12 or minus 12. Then you can solve again, add both sides by 12 and half them. So then you will have 12 over here. And then for the minus 12 cases, you have 0. So solving, we have xy in each case to equal to either 3 or 4. Of course, you can swap them by symmetry. and then we have 0, 7, or 7, 0. While for the other two cases, you will have negative numbers, which are -3, -4, or swapped, or 0, -7. Again, you can swap them. So the pairs in black should be rejected because I'm looking for non-negative integers x and y. So now we have these four pairs of solution, and we can check if it's a 3, 4 or 4, 3, then both sides will equal to 25. Whereas if one of the numbers is 0, then we have both sides to be equal to 49. So they are valid solutions. So this is the final answer to this equation. Here is my second approach to solve this equation. Firstly, I will separate into two cases. One is the very small one, and second is the main case to solve. The small case is that if either one of x and y is 0, or I can sum it up as xy equals 0, then 49 equals x squared plus y squared, because then the left hand side will be equal to -7 all squared. And we can see that x and y is either 7, 0 or 0, 7. And then we can move on to the second case, that if xy is larger than 0, because we're looking for non-negative integers x and y. If x and y are both positive, then notice that we actually have sum of squares equals to another squared. For x, y, and xy minus 7, we can actually construct a right-angled triangle with the length of the legs to be xy and that of the hypotenuse to be xy minus 7. This is because of the Pythagoras theorem. And we can call xy minus 7 as a Pythagorean triple. Then, since the Pythagorean triples, there actually exist two positive integers and both are larger than 0, or I can rephrase that there exist integers a larger than b larger than 0, such that x is equal to a squared minus b squared. At the same time, for the same a and b, y equals 2ab. And for the hypotenuse, xy minus 7 is equal to a squared plus b squared. There always exists such kind of integers, a and b, and both are positive. So I can put the equations on x and y into the last equation, and we have 2ab times a squared minus b squared minus 7 equals a squared plus b squared. And factorizing, we have 2ab times a plus b times a minus b equals a squared plus b squared plus 7. Now at this point, I'm going to do some bounding on the left hand side. So noticing that a and b are both positive, so b is the smaller one, I would say it's at least 1. And then a has to be larger than that, so a has to be at least 2. And we know since a is larger than b, I can also say that a minus b is at least 1. So now from this term is at least 1. While for 2ab, I can say is equal to ab plus ab. For one of them, I would say is at least a, while for the other, I can say it's always strictly larger than b, because I know that a is at least 2. But for symmetry, I will not say it's at least 2b. Instead, I'll just say it's at least b plus 1. So then I can sum up the bounding as since 2ab times a plus b times a minus b is equal to this, which is larger than a plus b plus 1 times a plus b times 1. So then therefore, we have a squared plus b squared plus 7 is larger than a plus b plus 1 times a plus b. The purpose for me doing this is that originally the degree of the left side of the equation, this expression has degree 4, which is hard to solve. I'd rather degenerate that into a polynomial of degree 2, like this, so it's relatively easier to handle. Then expanding the right side, we have a squared plus b squared plus 2ab plus a plus b. And so we have 2ab plus a plus b is at most 7. Furthermore, we know that under our previous assumption, a is at least 2 and b is at least 1. So I can say that the right side is at the same time larger than or equal to 2ab plus 3. Therefore, we know that 7 is larger than 2ab plus 3, and so ab is at most 2. But we know that from our bound on a and b, equality must hold, because when a is at least 2, b is at least 1, the product is at least 2. And so ab must equal to 2, a equal to 2, and b equal to 1. That's our only solution for a and b. Now we're going to put that back into x and y, and so we can conclude that x equals a squared minus b squared, which is 3, and y equals 2ab, and that's 4. Of course, we can swap the values of x and y, because, for example, we can simply let x equals 2ab instead of a squared minus b squared, and y to be a squared minus b squared instead. So we have 2 more pairs of solution, which are 3, 4, or 4, 3. So altogether, combining with 0, 7, 7, 0 as found above, again we obtain these 4 pairs of solutions, and this is our final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.